In the previous lecture, we have seen how to discretize the momentum equation and convert it into a linear algebraic equation, taking account of the nonlinearity coupling involving, for example, for the x momentum equation, the velocity in the vertical direction, in the y direction, and also the pressure at different points within the flow field. And we are able to take the x momentum equation in terms of the partial differential equation for a steady two-dimensional case, and we converted that at a particular point at the face of the control volume of a point centered around the point where pressure is evaluated. We are going to draw the diagram, and we said that at this point we could approximate the x momentum equation and convert that into an equation for the discretized momentum equation, which we wrote as sum over the neighboring locations where u velocity is evaluated times their respective coefficients times the neighboring velocity component equal to a constant b, plus, to be consistent with our notation on the PowerPoint slide, we have a coefficient times p dash e minus p dash capital P minus p dash capital E, because we have put a plus here, assuming A is a positive quantity. This is the discretized momentum equation, x momentum equation, on a staggered grid, which we identified like this. These are the major grid lines, the equivalent of I plus 1, I minus 1, I plus 2, j plus 1, j minus 1, and intersection of these is where pressure is evaluated, and vertically displaced half points is where velocity v velocity component is evaluated. Horizontally displaced midpoints is where u velocity is determined, so that the x momentum balance equation in its discretized form, involving, if we call this as capital P, east point, the west point, the north point, and the south point at which pressure is evaluated, then x velocity component is evaluated at the east face of a control volume centered around capital P, and it is also evaluated at the west face. V velocity is evaluated at the south face and the north face of this control volume. So this is how we have a staggered grid arrangement on which we discretize the x momentum equation to get velocities at points midway between pressure evaluations. And similarly, we can write down for from the y momentum equation v star n plus nb a and b, v star nb equal to, if we call this as be and bn, these are all coefficients, plus a north times p star capital P minus p star capital N. This equation can also be written, for example, A west u star w west plus sum over the neighboring values of A and B u star and B equal to B west plus A west times P dash W minus P dash P. So, the same template when it is used for the east face point, that is velocity at this point, looks like this. When we bring in the same template to a point at the west face here, small west, then the neighboring points are this one here, and halfway point here, and this point here. So, it involves the same computational molecule, just is displaced to the left here. So, we can write down similar discretized equations for every point at which we need to evaluate u component velocity, and like this for every point where we need to evaluate the v component velocity. And as we have seen in the previous lecture, these coefficients can be computed from using previous guess values, previous iteration values, and geometrical parameters like delta x, delta y, and physical parameters like rho and viscosity and other things. So, everything about these coefficients is known. The only problem is that in order to solve this, if we write down for all the points at which we have a velocity to be determined, then this equation and similarly this equation and all these equations can be converted into a set of equations like BU, where this is a set of linearized algebraic equations, and if we solve this, we get u star at all grid points. And similarly, we can take this one and convert this into a n v star equal to b v, and solving this will give us v star at all grid points at which v is defined. Okay. So, solution of these equations will give us the u velocity field and v velocity field. The only problem is that in order to find this u and v, we need to know p. We need to know p at every point. We can see that in order to evaluate ue at this point, we need p at this point and this point, and in order to evaluate u velocity at this point, we need pp and pw. So, in order to solve this equation, we need to know pressure at every point, and similarly we need to know pressure at every point. So, we can solve these things provided pressure is known. So, what we do, we guess pressure, we call this as P star because it is a guess pressure at all grid points. Okay, so that means that we know pressure at capital P, capital E, capital W, capital S, capital N for every point at which pressure needs to be evaluated. So, with this pressure field we can solve, for example, this equation 1 here and 2 here, and from these, from 1 we get u star and from 2 we get v star, but these are with the guessed field. So, that means that although we have made use of the Navier-Stokes equations, the momentum equations to get u here, the crucial pressure here is an assumed pressure field. So, that means that these are not necessarily correct solutions to the Navier-Stokes equations, and that will be felt when you substitute this in the continuity equation. So, these need not satisfy continuity equation. Because it has not been used, and these are with an arbitrary guessed pressure field. So, we say that let us correct pressure, therefore, by an amount p prime. So that means we write the true pressure value is equal to a pressure value, the estimated pressure plus a pressure correction P prime. So this pressure correction will vary from point to point. For example, at capital P we have the guessed pressure field plus a pressure correction. Similarly, the true pressure at capital E is P star capital E, which we have used for the velocity determination, plus a pressure correction which is at capital E. And we are saying that in the general case P prime P is not equal to P prime E. Okay, so that means that pressure correction needs to be evaluated at every point, and we are saying that let us make this pressure correction such that if we were to substitute Pp and Pe in the momentum equations, not P star P and P star E, but what we believe are the true values, then we would get a velocity corresponding u velocity and v velocity from these discretized equations, which are otherwise unchanged. So you have the same coefficients here, only instead of putting P star here we put actual corrected pressure, what we believe are the true pressures. So if we get this, then we get new values of u and v, and the new values of u and v should be such that they satisfy the continuity equation. Okay. So we require P prime, let us call this as xyz, because this is these are field values, to be such that resulting or corrected u and v satisfy continuity. Okay. So what we mean by this is we have the continuity equation, which is for two-dimensional incompressible flows can be written as dou u by dou x plus dou v by dou y equal to 0. Okay. Now we discretize this around capital P, location capital P, not at small e, not at small north, not at the faces, but at the point where we need to evaluate pressure, because we want to use this to get pressure. So we want to have this equation approximated at capital P. Okay. So for that, the staggered grid arrangement really helps us, because dou u by dou x at this point can be written as ue minus uw divided by delta x. So this can be written as ue minus uw by delta x is this point, this approximation for this derivative, and dou v by dou y at capital P here can be written as v north minus v south divided by delta y. We notice that here we are not putting any starred quantities, because these are supposed to be the corrected velocities such that they satisfy the continuity equation, and therefore when we substitute the correct velocities, then this should be equal to 0. Okay. So now here, along with the pressure correction, we are talking about a velocity correction. Therefore we are saying that just as we have true pressure is the starred quantity, the estimated quantity plus a pressure correction, we can say that the true velocity is u star plus a corrected velocity component u prime, and the true v velocity is the estimated plus a corrected quantity. And specifically we can say that at point small e, this is given by ue star plus ue prime, and Vn star, Vn is equal to Vn star plus Vn prime. And similarly, we can also write UW is UW star plus UW prime, and so on. So what we mean by this is that corresponding to when we introduce a pressure correction, there is also a velocity correction, and this velocity correction is specific to each location at which the velocity is being evaluated, and in the general case this velocity correction is not the same at all points. So now these are supposed to be the corrected velocities, and they are supposed to be satisfying the continuity equation. So we can substitute this expression here, and then we can write this as UE star plus UE prime is what this is, minus UW star minus UW prime divided by delta x plus Vn star plus Vn prime minus Vs star plus Vs prime by delta y is equal to 0. Okay, so the continuity equation tells us that this is the case, and in this equation all the starred quantities here are already known, because we started with a pressure values, guessed pressure P star, and then we have the discretized x momentum y momentum equation. We have solved this to get U star and V star at every point. So all the quantities that are starred here are known, and we can take them to the right hand side and write this as UE prime minus UW prime by delta x plus Vn prime minus Vs prime by delta y is equal to, for example, UW star minus UE star by delta x plus Vs star minus Vn star by delta y. Okay, so we have taken the starred quantities which are known onto the right hand side. We have this. So here we have got a different form of the continuity equation, which is still not useful for us because this won't help us solve for V prime and U prime. So what we do is that we try to write these velocity corrections in terms of the pressure corrections, because we know from the momentum equations that whenever we change the pressure, the velocity also changes. Okay, so and how can we do that? The true velocities and velocities that we have got will be satisfying the discretized momentum equations with the true pressure fields. So for example, if you substitute the true pressure field here, we can say that we can write the first equation as AE UE, no star anymore, plus sigma NB A and B UE UNB equal to B plus AE times PP minus P capital E. And similarly we can write this one here, A naught V naught plus sum over all the neighboring quantities at which Vn is being evaluated, A and B V and B equal to Bu and Bv plus Ae times Pp minus Pn. Okay, so we have called these as, we have not called these as anything. So let's subtract this from this and this from this one. So these are linear equations, so that becomes Ae times UE minus UE star, and we know that UE minus UE star is UE prime. So we can, by subtracting this equation here from this equation, we can write this as Ae times UE prime plus sum over the neighboring quantities of A and B, U prime and B equal to the pressure. This B will go away, and here we have PP minus PP star, so that gives us PP prime. Okay, PE prime. Similarly, we can write AN Vn prime plus sum over neighboring quantities A and B, V prime and B equal to AN times PP prime minus Pn prime. Okay. What these equations are telling us is that if we correct pressure field by a certain amount, which are given by this, these quantities here, there is a corresponding change in the velocity correction, and the velocity correction is given by this. Okay. So, if we are able to solve this, then we can put those things here. But in order to do this, we need to know this, and in order to know this, we need to know the velocity components. So, we can make an approximation, because we are only talking about corrections. So, there is a correction which is coming from the main point at which U is being evaluated, and a contribution from the neighboring quantities. All these things will balance the pressure correction. Okay. So, if you say that this is a discretized momentum equation, there is a correction to the momentum equation coming from the pressure component. There is a correction which is coming from the main velocity here, and also the neighboring velocity components are adding their own correction. In the true case where we have converged solution, then the velocity corrections are 0, pressure corrections are 0, because the converged case is where the calculated velocity field will satisfy the continuity equation. So, if that is the case, then there is no need for a velocity correction, and there is no need for pressure correction. So, since we are only talking about corrections, we can make an approximation. We can say that let us just cancel this, let us neglect this, and let us neglect this. Therefore, let us write that UE prime is roughly equal to AE by small a times P prime P minus P prime E. And similarly, from this we can get Vn prime is roughly equal to An by small a n times P prime P minus P prime n. And similarly, we can write the velocity correction at the west face is given by A west by A west times P prime west minus P prime P, and V prime south as being roughly equal to AS by AS times P prime S minus P prime P. Okay. So, now what do we have? We have some estimated velocity corrections, and we substitute those in this equation. So, each of these velocity corrections, induced velocity corrections, are expressed in terms of pressure corrections, and if we do that, we get, we have 1 by delta x times AE by AE times P prime P minus P prime E. So, that is UE minus UW is A west by A west times P prime west minus P prime P plus 1 by delta y times A north by A north P prime P minus P prime north, there is a minus, minus A south by A south and this whole thing is equal to 0. What is this? This is just the discretized velocity correction equation in which we have substituted systematically the velocity corrections by the corresponding approximate influence coming from the pressure correction. So, if you look at this equation here, we have delta x which is known, delta y which is known, all the coefficients capital A, small a west, all these things are known, and we have these pressure corrections at the grid points here as the unknown quantities here. So, this can be put when we write down for all the grid points. In this grid point, the variable that we are looking for is the pressure correction at capital P, because that is where we have written the discretized continuity equation. So, this is the one that is the unknown here, and we have minus here, minus times minus plus here, and then plus. So, we can write this as AP P prime P plus sum over neighboring quantities of A and B, P prime and B equal to some, it is not equal to B 0, it is equal to this whole thing, which we can call as BP. So, this equal to BP here. Okay. So, just as we have put here, we can write this also as AP P prime equal to BP. When we put this as system of equations, by solving this system of equations, we can get P prime. P prime for at all ijk. Okay. So, now what do we do with this P prime? Once we have P prime here, then we can make use of this approximation. Now, we know PP and PE, this is ijk and this is I plus 1 jk. So, we can get the corresponding U prime E, the velocity correction at the midpoint. So, that is we can get the velocity correction at U prime at I plus half jk, and similarly we can substitute Pijk and Pij plus 1 k here to get the velocity correction V prime at Ij plus half k. Okay. So, that means that we now have a pressure correction and a velocity correction for the two velocity components, and therefore, we can say that the new value of pressure is the old value of pressure plus the pressure correction, and new value of U is old value plus velocity correction, and new value of V is V old plus V prime. So, why do we say that this is new and this is old here? Because this P prime is not exactly evaluated, it is evaluated based on this approximation, based on neglecting this. Therefore, this is not an exact treatment. So, we can only say that we have improved upon a pressure correction. Okay, we have improved upon the value because we have taken into account contribution from the main thing, but not the neighboring things. So, this is already an improvement, and therefore, we can have this. So, the new value of pressure will not be the exact value, okay. But if you now put this back into this and then we redo this whole thing, get again new velocities and then new pressures and new velocities and new pressure. If we do sufficient number of times, then we will hopefully get a converged solution, and progressively the pressure corrections and velocity corrections will decrease, and progressively we find that BP here which is u star w minus u star e divided by delta x plus v star s minus v star n by delta y, this thing will become 0, because when the star quantities, that is when the old quantities approach the exact solutions, then this is the discretized form of the continuity equation, and discretized form of the continuity equation equal to 0. Okay. So, at convergence BP will go to 0. So, we will say that we will go until BP is sufficiently small, and then we can stop at that point. So, in the simple approach, we are making use of a semi-implicit approximation here, because the velocity correction here coming from the pressure correction is not evaluated fully implicitly. The neighboring components are being neglected here. So, we have a semi-implicit method for pressure linked equations is the acronym for this particular way, and what that particular way is that you start with a pressure estimated guess value of pressure at every point at which pressure is going to be determined. Okay. You substitute them in the discretized equations, and then you solve all the x momentum equations to get u star at all the grid points displaced by half a grid cell in the x direction, and then you put the same pressure field in the discretized y momentum equation and get velocity at all the grid points displaced vertically by half a grid point from the pressure locations. Now, you have u star and v star for a given p star, and you can directly go to this equation here. Okay. In this equation, BP is evaluated in terms of this u star and v star. So, BP can be calculated, and all these coefficients are part of the derivation. So, all the coefficients are known, and we can assemble this equation, and we can assemble this AP P prime equal to BP. So, this can be evaluated, and these coefficients are already evaluated here, and so we can get this equation. We have everything in this to be able to solve for P prime. So, we solve for P prime here at all ijk's, and using this P prime we evaluate u prime and v prime, and then we update our pressure guess pressure field and guess velocity field using some under relaxation factors. So, we put here alpha p and alpha u and alpha v. Ideally, alpha, all the alpha should be equal to 1. Okay. When alpha is equal to 1, then there is no under relaxation or over relaxation, but because we are looking at nonlinearity, because we are looking at coupling, and because we are looking at discretization, for all these reasons we would like to under relax. So, we would like alpha p to be between 0 and 1, and similarly alpha u to be between 0 and 1. Typically, you take these things to be around 0.6 and this to be around 0.4. Okay. So, something like that is a good thing, and this plus this must be equal to 1 is a rough guideline, is something that has been arrived at. And so, with the specification of this under relaxation factors, now you have everything that you require to complete one loop, starting with a guessed or old value of pressure. We get u star and v star, old values of u star and v star, which satisfy the discretized momentum equation with old pressure field, and using this old u star and v star we solve the pressure correction, and then we get pressure correction at every point, and using the pressure correction we evaluate the velocity corrections, and using this under relaxation formulas we update and get the new values of P, U and V at every grid point, and using this new values we can go back to the discretized x momentum and discretized y momentum equation and then get new values of u star and v star, and then new values of pressure correction, new values of velocity corrections, and then new values, updated values. So we keep on doing this in a loop, and we should be getting a solution in many cases. Okay. And in this method we have not made any approximations about the governing equations, although we have done it for a steady case. Something similar can be done for unsteady case, and although we have done for 2D, it can also be done for 3D. And I would like you to refer to more advanced material to look at this, or work it out yourselves for the 3D case and the time dependent case. So this is a strategy which has worked very well for a number of incompressible flows, and not just fluid flows, but also including energy, including reactions, and including lots of other complications for multi-phase flows and those type of things. Also a similar kind of strategy has been used, and although this method has been developed primarily for incompressible flows, it is also possible to take account of compressibility, compressible flows. And although we have explained this method for a staggered grid, it can be extended to non-staggered grid, but it requires some additional special way of evaluating the velocities. There is an interpolation scheme to get the velocity at this point, which is known as the Ricci interpolation scheme. Using this interpolation scheme to evaluate the velocities, it is possible to extend this method from staggered grid to non-staggered grid and avoid checkerboard oscillations. So in that form, this method has been used for all kinds of irregular flows using finite difference methods, irregular shapes using finite difference methods, and finite volume methods. So with this we will conclude the discussion of how to solve the Navier-Stokes equations. We have seen methods which have been developed for compressible flows, essentially mimicking the template that we have developed for a scalar transport equation, but adding extra features to take account of nonlinearity and coupling. And we have seen a number of other methods for the solution of incompressible flows, in which the linkage between the continuity and the momentum equations provided through the density term is no longer there. And we have a range of methods in this way to solve the Navier-Stokes equations, and we can say that it takes a lot more effort to solve the Navier-Stokes equations than to solve the simple equations that we have tried out in module 3. So to this extent we can say, yes, computational fluid dynamics requires some special techniques in order to get a solution. It is not like you have differential equations, so you can just solve it using any method. You need some specialized methods to solve fluid flow equations, and that constitutes the field of CFD. Okay. Now in the from next class onwards, we will go into another aspect of CFD, which is how to solve this A equal to B type of equations. And we can see that in this simple method itself, for the 3 equations, we have 3 times we have to solve Ax equal to B type of equations, and this is only for one update of the pressure and velocities, and we have to do it many times before we can get a solution. So we have to have an efficient method for the solution of Ax equal to B. Even in the case of compressible flows using beam warming methods and all those kind of things, again you have to solve similar type of equations. So in that sense, solution of Ax equal to B is something that will be cropping up again and again in CFD, and we need to have specialized methods so that we can solve this for large number of equations. So that is what we are going to discuss in module 5.